Hey everyone, welcome back to my channel. So what we're seeing right now is a Wikipedia page for bucket sort, but this is not what we're going to talk about in this video. Instead, we're going to look at the total daily visitor data for this page. Okay, we have the data, which is from 2019 to 2021. Okay, let's look at the time plot. Alright, so here's the time plot. This plot is made using Plotly, so we can hover on the graph and look at the value. The value is on the rightmost, on the right side. So like this one, it's October 29th, 2019. On that day, we had 340 people visiting this page. Okay, and we can see that all values are integers. Indeed, we won't see a number like 10.1 people visiting this page yesterday, right? And this is called count data because we are counting the total people visiting this page. And since we're dealing with time series, this type of data is also called count time series or integer valued or discrete valued time series. Modeling count time series is a bit different from continuous time series. So in today's video, we're going to study one of various models to accommodate the nature of count time series. Well, actually not only one model, but it all started from one basic model and then it is developed. It has several extensions. So yeah, there are so many extensions, but we're going to discuss only one extension and compare those models for this time series. Okay, let's study together. Alright, the first thing to notice was, well, this is count data, so all the data are integer. And then the second thing is that all values are larger than 0. Again, of course, this is very natural with the interpretation of the data. In the literature of count time series, this is called modeling for non-negative time series. And when it comes to count time series or count data, the first distribution comes to mind would be Poisson. So we cannot apply model that assumes normal distribution when the distribution of our data is clearly not Gaussian, it's clearly not normal, but instead either Poisson or any other distribution that falls into exponential family. Okay, so I said earlier that the first common distribution would be Poisson, but Poisson distribution has a limitation, and that is the mean and the variance has to be the same. But in count time series, it's very often that we have larger variance than the mean. It's called overdispersion. And this is what we have in this particular data set as well. In this particular time series, we can see in here, the variance is like almost, or maybe even more than 30 times fold than the mean. With such heavy overdispersion like this, I think, well, Poisson distribution won't suit really well. And so an alternative to that would be a negative binomial distribution. This distribution also in the group or in the family of exponential distribution. But the difference is that this negative binomial distribution allows overdispersion. Now let's look at the histogram of the data. So here it is. So this is the histogram of all values in the time series that we saw just now. And yeah, it's not normal, right? It's heavily skewed to the right and we have quite long right tail here. Actually, looking at this histogram, we can have an idea to assume a Poisson distribution into this time series. It's just that the rate would be high, or we can also assume a negative binomial distribution. So looking at this time plot and the histogram, we will use models that could assume Poisson and negative binomial and compare them. Okay, let's continue our exploration of the time series. So here's the ACF. The top plot here is the autocorrelation function, while the bottom one is the partial, or PACF, partial autocorrelation. First of all, we can see that the time series is non-stationary. Additionally, we can see seasonality. The seasonality component is really clear here. If we see here, it's every 7 legs. Since we're talking about daily data, that means we have a weekly seasonality. I also tried to make the ACF and PACF plots for the difference series, difference by only 1 leg. And yeah, even though these plots show that the non-stationarity is still there, but it's much reduced already. Okay, now let's look at the decomposition of this time series. Yeah, I assume that we really do have a seasonality, weekly seasonality. So therefore, I set the frequency to be 7 when I make a time series object. And so, yeah, it's like this. Alright, now that we have explored the data a bit, I want to try to use INGARCH model, because INGARCH model is designed for integer value time series. And INGARCH model can be used with Poisson or negative binomial distribution. Okay, now let's dive into the model. The model is called INGARCH, or integer valued GARCH. Well, we do have a model named GARCH. So GARCH is here general autoregressive. R is for AR, autoregressive, and then conditional heteroscedasticity. So it might seem like INGARCH is an extension of GARCH, but specifically designed for integer valued. Well, to a certain extent, it might have some similarities in a way that they have hierarchies. But I don't know, I feel like INGARCH is more similar to state space models rather than to GARCH. Because in GARCH, we focus more on modeling the random error, the variance of the random error. While in INGARCH, it's not the case. In INGARCH, we will assume some conditional distribution on the observed value, and then we will model the mean of that conditional distribution in the next layer or the next hierarchy. When INGARCH was first developed, it used Poisson. That was in 2006, and then 3 years later, a negative binomial distribution for INGARCH was developed. And so we're going to use both of them. Okay, by the way, INGARCH here, well, the complete notation is INGARCH of order P and Q. P is the order of autoregressive, while Q is the order for moving average. Okay, now let's first assume that the conditional distribution is Poisson, so the notation would look like this. Each value in the time series, given all the information we have so far, follows a Poisson distribution with the mean or the rate lambda t. What's in the information set? The information set comprises all y's and lambda values from the beginning, so time t equals 0 to time t minus 1. And if you want to include a covariates, the covariates at time t are also incorporated. Okay, in negative binomial distribution, we have the parameters mean and the dispersion parameter. Okay, the notation is almost the same, it's just that the distribution now is changed to negative binomial. Now, we might be more familiar with the parameterization of negative binomial as R and P. R denotes the number of successes, and P denotes the probability of success at each trial. Because negative binomial is really related to binomial distribution, like Bernoulli trial binomial distribution and such. But in regression tasks, or well, in modeling tasks basically, it's simpler to use alternative parameterization. We have several alternatives to R and P, and one of them is the mean and dispersion parameter. And this is what we're going to use in this project. From the practical point of view, I think it makes sense if we want to use the alternative parameterization for negative binomial by using lambda, so we have more similarity with the Poisson distribution. So when we implement it, we can just use one function and just tweak a little bit to switch from Poisson to negative binomial distribution. Furthermore, as I said earlier, INGARCH model works like a state space model. It has hierarchies. So we will need to model the lambda here. Therefore, if negative binomial is parameterized as R and P, it will be hard to model them further. It's hard to say which one to model in the next layer. Is it R? Yeah, probably R, but it's a bit less intuitive, I guess, because by using this framework, we can see the time series as if like we have the observed hierarchy and something in between that works as a motor, if you will. Okay, before we dive into the modeling for the lambda, let's look at the nature or the some properties of Poisson and negative binomial distribution. So first of all, here are the PMF or probability mass function for both distributions. This is gamma functions. Okay, so a gamma function of A for all integers, for all positive integers A is defined as A minus 1 factorial. Okay, and now look at this. The mean and the variance of Poisson distribution is the same, which is lambda t. And this is the main restriction of Poisson distribution. It requires the time series to be equidispersed. While in most, it's very common in count time series, and we already saw our time plot as well, they are commonly overdispersed. And if we look the mean and the variance of negative binomial, it's clear that the variance is larger because of this extra term. Yes, so the variance of a negative binomial distribution will always be larger than the mean. One note on the variance here. Some people like to write it as lambda t plus the overdispersion coefficient. I'll denote it as sigma squared times lambda t squared. So the overdispersion coefficient is related to the squared mean. I'm using sigma squared to denote coefficient of overdispersion. This is following the vignette of the R package that we're going to use. Okay, and what's the relation between phi, the dispersion parameter here, and the overdispersion coefficient? Here it is. The overdispersion coefficient, sigma squared, is 1 over phi. And notice that, maybe I should erase the inks for a second. Notice that if the phi here gets larger to infinity, then this term would be 0. We won't have this term, and therefore the mean and the variance would be the same, just like in Poisson distribution. So actually, Poisson distribution is sort of like a special case of the negative binomial distribution. Okay, now we're ready to model the mean. Notice that now we have the same notation for the mean of both distributions. So the conditional mean, regardless of our conditional distribution, would be modeled this way. One note is that this works if we have identity function. In other words, this is actually from the generalized linear model form. So it's supposed to be, like the lambda is supposed to be put into a link function. Let's name the link function as g. So yeah, g of lambda t. And then yt is also put into a link function, a transform function. Let's say that it's called g tilde of y t minus I. But assuming that we are using identity function, so that the link function of lambda, the results of that would be the lambda itself, this equation is what we're going to have. Okay, now let's look at this equation in more detail. This first term is the intercept, and then the second term is the past or the lagged observations. P here is the order of autoregressive. But actually, in practice, in the coding section later, we will see that it's not going to go from 1 to P. Like, for example, if P is 5, then it's not always going to be 1, 2, 3, 4, 5. Okay, it's not always like we will have 5 parameters just for autoregressive. The point is that how many lags we want to use, how many lags of observations we want to use. Okay. It's probably more accurately to say that P is the total lags that we want to use, the total the total past observations. Yeah, that's it. The total past observations we want to use. And then for the third term, this is for the moving average part. Okay, now some constraints for this modeling, for this equation. The most important is that all betas have to be positive. Okay, this is to ensure the positivity of the conditional mean. Additionally, P has to be larger than 1. Larger than or equal to 1. While Q has to be larger than or equal to 0. Alright, now this modeling works if we don't have covariates. If we want to use them, we can do so by adding the fourth term, just here. This is the dot product between the covariates and their respective coefficients. The coefficients are put into a vector eta. And so, well, more formally, eta is like this. It's an array with length r. And notice that here we just use xt. That means the covariate at time t to model the conditional mean at time t. While for the past observations and the past conditional means, we might want to use more than one for them. Okay, now back to our project for a second. What is R? In other words, how many covariates we have? Okay, so for our project, since we have the total daily visitor for Wikipedia page of bucket sort, our covariates is the total daily visitors of Wikipedia page that leads to or that mentions bucket sort. We'll see in a moment that we have 17 pages that mentions bucket sort. So yeah, R would be 17 in this case. Alright, now how do we predict all of those parameter values? We are going to use maximum likelihood estimation. That is if we believe that the true distribution of our data is Poisson. Otherwise, if we believe that negative binomial distribution suits better, we will use quasi-MLE. Why is that? So you see, the difference between quasi-MLE and the real one is that we will only use MLE if we believe that our assumption on the distribution is the real one, it's true. So in this case, we will use MLE if we truly believe that, or like maybe somehow we know that the true distribution of the data is Poisson. With quasi-MLE, we allow some specification in some parts of the distribution. So by implying QMLE, we actually allow misspecification in the dispersion parameter. Okay, let me explain that. So if we want to use MLE only for both distributions, let's say Poisson first. We believe that the distribution is Poisson, and therefore we set a likelihood function that's based on Poisson and estimate the parameters. If we believe that the negative binomial is the true distribution, then we need to make a likelihood function that's based on negative binomial, right? And that's going to create a different likelihood function. So we will need to use two different likelihood functions. It's like the right way to approach this problem. But to simplify things a little bit, we can just use one likelihood function, estimating the same parameters, and then using those estimations, we estimate the parameters that we haven't estimated. In this case, we use the first estimations like the betas and the etas and the intercepts, and also the lambda, and then use them to estimate the dispersion parameter. And I think we can do this because it's claimed that the estimated parameters does not depend on the dispersion parameter. So it's like we need the over-dispersion coefficient to define the negative binomial distribution, but we can estimate it later. Now, finally, let's talk about the parameter space. What is our parameter space? Now, let's look at this equation once more. So we have the intercept, and then we have P lex that we want to use, and then we also have Q lex for the conditional mean, and lastly R covariates. Okay, so the total parameters would be equal to P plus Q plus R being the total covariates, plus 1. This is the total parameters that we need to estimate regardless of the distribution we want to use. Alright, back to our R studio. I plot some of the covariates. So here it is. Even though the colors are like they are in pairs, but no, it's just a coincidence. Okay. Anyway, so 4 of the covariates are bubble sort, and then computational complexity theory, sorting algorithm, and time complexity. So if we search, or if we got into the Wikipedia page of time complexity, there must be the bucket sort hyperlink there, which leads to the bucket sort page. And I make the correlation plot here so that we can see right away the correlation between covariates and between the covariates and the bucket sort, or our time series. So our time series is labeled as Y, and it's in the top row here. And we can see that the largest value is 0.93. We have two variables with correlations 0.83, and the second largest correlation is 0.81. And if we see these three, these are insertion sort, merge sort, and heap sort. And here we can see all the covariates named, by the way. Well, either in the x-axis or the y-axis. And it's interesting to look at this correlation plot because all the correlations are positive. So they are positively correlated among each other. Okay, now we're getting closer to the modeling. Before we do that, I want to split the data. So we split the data into training and validation, or testing actually, but I just name it validation so I can denote it differently. T into FT denotes training, while V denotes validation. So the data I'm using for validation is the last 15 days, so all data in March 2021. And actually we can verify that the length of YV is 15. Yeah. So we're going to predict the total daily visitor for bucket sort for 15 days. I'm going to show you how I predicted. It's actually just a recursive prediction. But yeah, we'll see that at the end. Okay. So now let's start the modeling. I will fit several models. First of all, as I said earlier, that I'm going to try to assume both distributions. So the Poisson here, model Poisson and C and Poisson are assuming Poisson distribution, while the rest of them, NB, model NBC, model NB, and model NB3C, are using negative binomial distribution. I give the code C to tell me that I'm using covariates. Okay, and 3C here is that a model that uses 3 covariates, namely insertion sort, heap sort, and merge sort, the 3 covariates with the highest correlation with our time series. Okay, so to fit the model, this function tscount is basically initialize the model and fitting right away. As you can see from the pop-up, those are the parameters. The first is the TS object. Oh no, sorry, not the object, but the time series. So we're putting in YT, and then the model is put as a list. So how do we want to specify or define the model? And then the next one is xrec. Xrec is for exogenous variables. This is where we put in our covariates. The default value is null, so the default model is an INGARCH model without any covariates. Okay, and then the parameter link is about link function. And in the theory section, we assume that we are using identity link function. And that's the default value actually, so that's why I don't specify it further. And then for the distribution, it's either Poisson or Binomial for negative binomial. The default is Poisson, so if I want to assume a Poisson distribution, I don't need to specify it further. But for models with negative binomial, I need to set it again. Okay, so let's look at the first model. So the first model is named model Poisson C. That means I'm going to use the covariates. And now let's focus ourselves on the model parameter here. In the theory section, we model the lambda or the conditional mean as the intercept plus some terms for the autoregressive plus some terms for the moving average part and plus the dot product between the covariates and their coefficients if we use them. Past observations is the lags that we want to use for the autoregressive because we are regressing the value at time t on some past observations. And then for the past mean, it's using the lags for the conditional mean. In other words, the moving average part, or the third term in our equation there. For the past observations, I want to regress the value at time t on the first and sixth lag. Okay, so yt minus 1 and yt minus 6. While for the past conditional mean, I want to use the seventh lag. So lambda t minus 7. So we only have two beta values for the autoregressive part and one beta value for the moving average term. And why do I use these values? Let's look at our ACF and PACF plot again. So here it is. In classical modeling, the order for autoregressive can be determined by looking at the partial autocorrelation plot, which is the bottom plot here. And here we can see that the PACF, the highest PACF is on the leg 1, and then the second highest is on leg 6. It means that xt or yt, because we denote our time series as y actually, right? So yt has the biggest correlation with yt minus 1. So for example, we have two time series. The first is yt, and the second one is the first leg of yt. It's just like shifting our time series by one time step. Those two time series have high correlation. And the second most correlated is with yt minus 6. Maybe we can plot this actually. Let's try plot. So we want to plot yt with yt from 2 to the length of yt. We can see it's quite correlated, right? It's not scattered randomly, but rather like making a correlation. And now let's do that with the sixth leg. It's quite correlated as well. It's looking like it's making a line. But let's say that we are trying to plot the yt and maybe this one, leg 25. Okay. The value here, the PACR value here indicates that we have a small correlation between yt and its 25th leg. Okay, and let's see. It looks random. It doesn't look really correlated. Okay, so that's why I'm using leg 1 and 6 for my past observations. And then for the past conditional means, it's about moving average, and we can determine the moving average order by looking at the ACF plot. Actually, looking at the ACF plot, we can see many significant values. But since we're talking about moving average about the conditional mean, I want to try to capture the seasonality by using the conditional mean. So since this is a weekly seasonality, I'm just using the past mean of leg 7, so only one value. So here we are using p equals 2. Well, not equals 2 in the sense like it's an AR of p, but we are using leg 1 and leg 6. And then we have 1q, so making the total of 3. And then plus 1 intercept, and then plus 17 covariates. So we have 21 variables. Okay, we are done training the model Poisson C, the first model, and it gives us a warning message. It says that at least one estimated parameter is very close to 0. So it's saying that the model constraint is almost cannot be fulfilled, cannot be met, because we saw earlier in the theory that we need to have positive parameters. Okay, but for now we'll just ignore this. Okay, now let's move on to the next model. The next model is still using Poisson distribution, but I am not using the covariates, so this would be a univariate time series modeling. The model is still the same. Actually, the model specifications are all the same. This will help us in comparing the performance of these models. Okay, let's train this one. Okay, we are done training the second model. By the way, let's look at model Poisson C. We can see the result of the model more neatly by using summary. the summary function. Okay, so here is the, well, general information. The AIEC and BIEC are, well, QIEC too, are around 21,000. We will see later that, we have some models that perform much better than this. And by the way, these are the estimates for the parameters. The intercept is beta 0 in our theory slides. And yeah, it's estimated to be 269. And then beta 1, beta 6 are the autoregressive parts, while alpha 0, alpha 7. Alpha 7 denotes the moving average part, or like the conditional mean part. Okay, and then let's see the model Poisson as well. Here in model Poisson, since we're not using covariates, we have much fewer parameters. We only have 4 because 1 intercept and then 2 beta for the past observations and 1 alpha for the past conditional mean. And we can see that these scores are much lower than those for the previous model. Oh, actually, it's also stated here the number of coefficients, 4, and then the log likelihood. In the previous model, the log likelihood was minus 10,000, but here we have minus 5,900, almost 6,000. Okay, now for the rest of the models, we are using negative binomial distribution. Now, when I'm recording this, I already know how these models performs, right? And actually, in the process of making this video, I tried these 4 first and then compare them. And coming out from these performance, I tried a new model, which is the negative binomial distribution and including only some covariates. I think there's no point of trying using Poisson distribution anymore. So in model NBC, I'm using all the covariates. That's why when I set XREC, I just set it to be DFT because I'm going to use all the columns anyway. While for model NB3C, I'm using only 3 covariates. So I have to specify which columns I want to use. And I'll show you in a moment that the insertion sort, heap sort, and merge sort are in column 11, 12, and 13. Okay, we are done training all the models. Since we include some models with covariates like model NBC and model NB3C, we get some warning messages again. One warning message is about the parameter for the covariate is near 0, and the other warning message is about the estimated intercept that is very small. Okay, let's look at which one cuts which warning message. I think it's quite obvious. I think model NB with all covariates have at least one estimated parameter that is near 0. The estimated parameter, or like the alpha, the coefficient for computational complexity is near 0 here. Okay. Model NB3C, so the negative binomial distribution model with 3 covariates, have very small intercept. Here's the sigma squared. It's not the variance, okay, but it's the overdispersion coefficient. And here we can see that the overdispersion coefficient is quite small actually. For the negative binomial distribution model with all covariates, let's look at the overdispersion parameter is, wait, where is it? So I don't know why we cannot see the sigma square value here, but if we just run the model without the summary function, we can see that the overdispersion coefficient is 0.07. Okay, now let's compare these models. First of all, I have collected all the AIC and BIC scores. So these are the AIC and BIC scores for those 5 models that we trained. We can see that the models using Poisson distribution have much higher scores than the ones using negative binomial distribution. And with AIC and BIC scores, we want to get as low score as possible. So based on that, it seems like negative binomial is more suitable for this time series. So earlier I had a guess that this could be a Poisson distribution with high rate, and the other guess was this is a negative binomial. Now I think we can safely rule the Poisson distribution out. And then among the models using negative binomial distribution, we can see that model NB with 3 covariates have the lowest AIC and BIC scores. Now let's compare the ACF for the residuals. This can help us seeing whether the residuals are stationary or not. Okay, interestingly, the Poisson covariates. So Poisson covariates is the model POS C. Okay, and then negative binomial covariates is the model NBC. Those models are clearly not stationary. In fact, the ACF of these residuals look very similar to the ACF of our original time series. But for the others, well, they look quite nice. It seems like the seasonality are not, there is still some seasonality left in the residual. Maybe we should have included more legs in the conditional mean. Okay, now move on to the next one. Now, with count time series, another metric that we can use is called the probability integral transform. So this will give us plots, a histogram actually. And the model that is suitable for our time series will give us a histogram that resembles a uniform distribution. So the histogram should be a flat histogram instead of like a histogram of a normal distribution or of a Poisson distribution. So now let's look at these results. For the models using Poisson distributions, they look like U, so it's also called the U-shaped histogram. Okay, and then for the negative binomial model that is using all the covariates, it's not looking so great because we can see like it's going down, the histogram is going down. In my opinion, either model NB, which is the negative binomial here, or negative binomial with 3 covariates, so model NB3C, resembles more like uniform distribution. Okay, let's see another comparison. Maybe, we will have a better idea of who's the winner. So here we are making a data frame of the scores, so scoring of those models. So it's basically a data frame of several scores or several metric values, such as the logarithmic error, quadratic error, and then normalized squared error, and then squared error. Okay, and then the spherical score and others. Except for the normalized square error, we want all the other scores to be as low as possible. And then for the normalized square error, the suitable model will have the value really close to 1. In other words, the closer the value to 1, the more suitable the model is. And as you can see, the order of the models is the same as how I fit them. So Poisson with covariates, and then Poisson without covariates, and then negative binomial with all covariates, and then negative binomial only, and then NB without NB with 3 covariates only, okay? We can see that these results are quite consistent. The negative binomial 3C is the lowest for all of these scores. Here is minus 0.09, and then this one is 20, and then this one is 8.24, and this one is 1,500. For the normalized squared error, though, model NB has a higher score than model NB3C. Alright, so now we have two finalists, if you will. I can't really decide which one is better, whether it's model NB or model NB with 3 covariates only. So I'm going to compare these finalists and use them to predict the 15 days in the YV. Alright, so yeah, it's a recursive prediction. It's an iterative process. So for the first iteration, I'm going to use all the data in the training time series to predict the next day's total visitor. And then I'm going to take one value, or the first value in YV. So that's the real data in the validation time series. And I'm going to add that to our training. So the training data set would be one data longer, and then train them again, and then use the trained model, the new trained model, to predict the next day, and so on. So yeah, I know it's going to be really slow, but yeah. I'm going to first forecast using model NB. And so we will see that the predictions using model NB are going to be denoted by blue colors. I'm going to show you in a moment what they are. And for the model NB3C, I'm going to use the pink colors. Okay. Wait, did I run this? Let's run this. Okay. And then, yeah, let's run this. Okay, while waiting for our predictors, let's go through the function, our forecast function, just briefly. The important thing I want to talk about in this function is the forecast values. Okay, we will take two forecast values. The first one is the mean forecast, and the second one is the coherent forecast. Okay, so there's this notion of coherent forecasting in count time series, and that is using the median instead of the mean for our forecasted value. The mean of a distribution from a count time series might not be an integer, but the median and the mode must be an integer. Since we're talking about count time series, we're talking about non-negative integer, it wouldn't make sense if we forecast the next day's daily visitor to be 250.9, right? Of course, we can round it up to make it integer, but, well, we can just use the median of our forecast distribution, and take it as our forecasted value. Furthermore, the median of the forecast distribution is the value which minimizes the mean squared error. So this is why I want to try to forecast using two different ways. The first one is the mean, which is taken from the prediction method. Like the prediction value that is generated by using predict function. Okay, so we have the model, and then we put it into our predict function, and we will have several names. We will have a list with several values, several names, and by taking the prediction, we take the mean of the forecast. And then we also have the median, and that's what we take to get our coherent forecasting. Okay, so here we are. We are done with our forecasting. If you see two windows here, the first one is for the warning messages. Okay, now let's look at the plots. Again, the blue lines, the dark and light blue, are for model NB, so the negative binomial distribution without any covariates. Whereas the pink, the dark and light pink, they are for models that assumes NB distribution but also including 3 covariates. Okay, and as we can see, the univariate model is clearly better than the ones that using covariates. So I guess based on this graph only, we can say that the winner is model NB. Now let's look at the difference between the forecast from the mean forecast and the coherent forecast. Yeah, they're really similar for both models. So maybe coherent forecast is a better alternative because it makes more sense. Let's zoom in. And I'd say the prediction is quite decent. The direction, it predicts the directions quite well. Of course, I think there's a lot of room for improvement here. We can play around with the order, with P and the order, like the legs that we want to use. And then we can also maybe add covariates. And by the way, I want to make some notes about the models which include covariates. In the vignette, it said that there's no thorough analysis on models which include covariates actually. So that direction is still very open to future research. You can look at their analysis of how they want to estimate the model, to estimate the parameters by including the covariates, and how the stationarity goes, the stationarity of the models that use covariates. And judging from this project alone, it seems like maybe INGARCH model works better for univariate time series. Okay, so that's it for this video. Thank you so much for watching. I hope you enjoyed this project. Please consider subscribing to my channel, and you'll see this code uploaded in my GitHub. I'll see you next time. Bye bye.